We'll get our homework right away on page 613. We've had 1 to 3, 7 to 11. I'm pretty sure we're going to have to go over number 10. Any other issues besides number 10? Nine. 9 and 10? Any others? Going once, going twice. Okay. 9 and 10 today. Number 9 says the battery supplies a current of 5.2 milliamps. 5.2 milliamps in the circuit, determine the quantity of charge that flows in the circuit for 2 seconds. So we've got a current here of 5.2 milliamps. We've got a time of 2 seconds. We're looking at the charge, looking for Q. Which equation is it exactly that we're going to use to find the amount of charge given the current, given the time vector? Q over T. Okay. I is equal to Q over T. Now, we're going to have to rearrange this to solve for Q, but that's the easy one, right? I didn't think the T to the other side and get Q by itself. Multiply here. I times T. So it becomes I, 5.20 times 10 to the minus 3 amps. We're not going to forget to convert that to amps because we circled that way into that. Time is 2 seconds, and multiply that together, we're going to get about 1.4 times 10 to the negative 2. Is that right? 1.4 times 10 to the minus 2. So that would be number 10 is a tough question. It's a really tough question, actually. With the 2 conducting wires, they're carrying currents in opposite directions. We want to know whether they attract each other or repel each other. I'm going to draw that out. I'm going to draw one of them going into the page and one of them coming out of the page. Draw the magnetic field that surrounds them now. Or at least one magnetic field. There's lots of field lines that surround them. We just need to draw one to show the direction. The magnetic field surrounding the first one is going to be counterclockwise. We know it's going to be counterclockwise because we use the left-hand wire grasp rule. Follow the direction of the particles and the figures point counterclockwise. Similarly, on the right one, it's going to point clockwise. Right? Following the direction of the current, which is out of the page, figures go in the direction of the field, which is clockwise. That still doesn't tell us whether they attract or repel them. So what we want to do at this point is pretend we have magnets. We can deal with attraction and repulsion with magnets a lot easier than attraction and repulsion with wires. So let's pretend we have magnets. Let's draw a little pretend magnet up here. Let's draw one right here. If we do that, we're going to find that this would be the north pole of that pretend magnet, and this would be the south pole. This would be the south, and this would be the north. How do you know that? How did I say that that's the south pole and the north pole? These are the pretend magnets. Yeah, the magnetic field inside the magnet goes from south to north. If you want to think of it as outside, the magnetic field is going to go from north to south. Outside the magnet. So whenever you look at it, inside the magnet, south to north, outside the magnet, north to south, the way you look at it, we're going to find how everything is the way that I show. Now let's take a look at those 2 pretend magnets. Those 2 pretend magnets look at each other and determine if they're attracted or repulsive, which is just looking at wires. Do these 2 magnets attract each other or repel each other? Look at it. It's south against south, these 2 magnets are going to repel each other. These 2 magnets, these 2 pretend magnets are going to repel each other. These wires that cause them are going to repel each other. Now, how do you know to draw these little pretend magnets at the top? How do I know not to draw them down here? Well, let's try drawing them down here and see what happens. This is going to be south, this is going to be north, this is going to be north, this is going to be south. Those 2 magnets are also going to repel each other. So it doesn't matter whether they're going to be at the top or at the bottom. What if I had drawn them right here? Field goes from south to north inside, south to north inside. These 2 magnets are going to repel each other as well. Not only do we have north and north, we also have south and south. No matter where you put them, these 2 pretend magnets that are drawn in are going to be repelling each other, repulsive forces. So therefore, the 2 wires in the cross are going to be repulsive forces. Is that okay? I've given a question like this on a test before. I can't remember if it's on tomorrow's test. So it's really up a little bit. But there's been a question similar to this on the test before. I I would say it's probably about a 50-50 chance of something like that being resistance to that. Simply because it needs to be one. Okay. All right, I want to spend a couple of minutes now reviewing what we did yesterday. That's the whole idea of induction and introduction, and that new concept that we learned in law. Electromagnetic induction, the generator effect. Call it what you want, it means exactly the same thing. Let's rewind it a little bit for a second. Orsted, in the year 1890, he discovered that the electric current or moving charges will generate a magnetic field. Fast forward 12 years, two guys, Michael Faraday and Joseph Henry, in the year 1832, I believe it was, they discovered what essentially amounts to the converse of this. The magnetic field can generate an electric current. There are no conditions on Orsted's discovery. If you have an electric current, you will have a magnetic field, no matter what. There are conditions on Faraday and Henry's discovery. Magnetic field can generate an electric current, but it doesn't always. One of three conditions has to be met. Those three conditions are as follows. Number one, you got a wire, you got a magnetic field. If the wire is moving relative to a magnetic field, then you're going to get a current. The second condition says if the magnetic field is moving relative to the wire. Now, it doesn't really matter, of course, which one's moving. In fact, we often don't even distinguish between these two conditions, condition one and condition two, because they're really not the same thing. As long as they're moving relative to each other, you will get it. The third condition is a bit different, and it's the one that most of us have. If you have a changing magnetic field is getting stronger or weaker, or some sort of combination of both, stronger than weaker, and stronger than weaker, we're going to change it. The one we focus on most is condition number one. But remember, the condition number two is really just the same thing. We don't spend very much time at all. Why is it now that when you move a wire to a magnetic field, we're going to generate a magnetic current? Let's rock it. We've got a magnetic field that's produced by these two magnets moving in the south. That magnetic field goes from north to south towards the right side of the page. Let's say we've got a wire being that magnetic field. Now that wire isn't moving. It doesn't have an electric current in it. It's just a plain, straight piece of copper wire. It's got electrons in it. But it's got electrons in it just the same as your shoe has electrons in it, and your shirt has electrons in it. Everything is electrons. It's wired to it. This wire with the electrons in it, sitting there in that magnet. Now, if I push that wire in a particular direction, I can cause those electrons to start moving. So let's say we're going to push that wire out of the page. We're going to push it towards you guys. We push the wire towards you guys. That means these electrons are now moving towards you guys. Not because of any kind of crazy electric force or crazy magnetic force, simply because I pushed it towards you guys. But they're still moving. Anyone who look at it, they're still moving. Let's figure out left thumb in the direction these particles are moving out of the page towards you guys. My fingers are going to point in the direction of the external field, which is from north to south. Thumb out of the page, fingers from north to south. My palms are going to point downward. That means there's going to be a magnetic force on these electrons moving downward. That's going to cause these electrons to start moving within this wire. They're going to move down toward the bottom of that wire. that make sense? So we knew that when we push hard, we feel perpendicular to that is really careful. Now we know the law. Because of the force that acts on you is the wire. The force that acts perpendicular to the motion of the wire itself, which causes the electrons all to the wall. All right. We also talked about Lenz's law a little bit yesterday. We didn't get a lot of detail on it. We talked about it with the games, but I hope it makes sense for the next 5 minutes. The demonstration yesterday involved dropping a magnet to a copper pipe. That magnet accelerated downward, but at a much lower rate than its steel acceleration. We learned that because it was a magnet, but the magnet's not attracted to copper. So why was it that happened? It goes back to electromagnetic induction. It goes back to what Ørsted and Göring taught us in 1992. I'm going to give you a little bit of Lenz's law here now. Notice I'm not erasing everything that I wrote down. Ørsted and Göring is how we're going to do it. Because that's going to form part of what we're doing now in Lenz's law. Faraday and Henry would have said that when a magnet moves through a conductor, which that copper pipe is a conductor, then we're going to generate an electric current. So that's what happens. So when it drops that magnet through the conductor, we generate an electric current. Moving magnet generates an electric current. That's that second condition that we learned with electromagnetic induction. First one was move the wire, generate a current. The second one was move the magnet. We're dropping the magnet, gravity's pulling it down, magnet's moving through the conductor, and current in that cup. Now that current wasn't strong in the field, even though I was holding the copper pipe, it wasn't strong enough to move the magnet. It was there. Now Ørsted would have said, you've got an electric current, it's going to generate an magnetic field. Understand what we have here. We have an original magnetic field. The magnetic field that we dropped, magnets we dropped into that bucket. Now we have another magnetic field. The magnetic field was just produced by an electric current. That was produced by that electric current. I'm sorry, that one is stagnant. That was produced by the original magnetic field. So the magnetic field makes an electric current. That same electric current makes another magnetic field. Now we've got these two magnetic fields. So far, so good. Really, all we've done so far is Ørsted and Faraday, right? Magnetic field makes a current makes a magnetic field. Now we have two magnetic fields. And here's the big thing with Lenz's law. The two magnetic fields that we have, that's the original one that is moving through the pipe. And the new one that we have, the one that's produced by the current, that was produced by the magnetic field. These two magnetic fields always act to oppose motion. They will attract each other, or they will repel each other, or do what they need to do in order to oppose the motion of the magnet. Drop the magnet, gravity tries to accelerate it down at an angle to it. There's an opposing force pushing up. An opposing magnetic force pushing up. It comes as a result of these two magnetic fields. The same thing would happen if we had chosen to take the magnet and suspend it and then drop the coil or drop the pipe. The same thing would happen. You would have had a magnetic field producing a current. Now, not because it moved the magnetic field, it's because it moved the coil or moved the wire, or moved the button. It doesn't matter which one moved it. You move the magnet through the pipe, move the pipe around the magnet, it isn't doing exactly the same thing. So if you had to drop pipe around the magnet, then we would have found that the current was still producing the pipe. That current would have produced a second magnetic field, and that second magnetic field would have acted with the first opposing motion. This time not on the first diagram, but opposing motion. Now, why does it have to be an opposing force? You must oppose. You can't help it. You can't speed it up. And when we drop that magnet to that point, it's not going to accelerate at 12.5 meters per second squared. It can't. It has to be a little lower than 9.1 because it has to be an opposing force. But why does it have to be an opposing force? So there's a very particular fundamental law of physics is violated. The law of conservation of energy is not violated. If we hold a magnet up, it's got a certain amount of gravitational energy. We drop it, and it's going to gain kinetic energy. The closest amount of kinetic energy that we can have is reaching the bottom is going to be the amount of kinetic energy that I know is at the top, right? So you have 10 joules of potential energy from the start. The most kinetic energy we have is 10 joules. Well, if this apparatus caused this magnet to speed up at a rate greater than negative 1, it would have more than 10 joules of kinetic energy. It might have 15 or 20 joules of kinetic energy. Where did it come from? You can't create kinetic energy from nothing. You start off with 10 joules of energy. You got to end off with 10 joules of energy, or less. Something somewhere else. You can't get energy from nothing. So, if it isn't opposing, if it caused it to speed up at a rate greater than 9.1, that's what we violate that fundamental law of conservation of energy. Kinetic energy would be off a piece of steel. None of this applies. Off a piece of steel. All we had was a piece of steel moving through a conductor. That doesn't generate a current. And that doesn't generate another magnetic field. You have to have a magnet in a conductor moving around, not a piece of steel in a conductor. That makes sense. So what I'd like to do right now is send out a practice quiz. It's a quiz that I was doing before your class. We didn't have on the stuff yesterday in time. I'm going to give you a quiz now. I'm just talking about this quiz. I'm going to ask you to do questions 1 and 2 on the demonstrates over the next week. After that, I'll ask you to go through 4 on that quiz. And then we'll take a look at questions 3. All right, take a look at number 1 and number 2 from the quiz. Number 1 says the vertical antenna of a vehicle will generate the greatest induced voltage, the greatest induced potential by the Earth's magnetic field if the vehicle moves in this way. Everything in magnetism seems to come down perpendicular. Everything's got to be perpendicular. So if you want to induce the greatest potential difference, you want to travel perpendicular. You want that antenna to go perpendicular to the Earth's magnetic field. Yeah. This magnetic field goes from magnetic north to magnetic south, from Antarctica to Canada. It's going to go that way. If you want to reach the greatest potential difference, if you want to either drive your antenna that way or that way, you want to drive it either east or west. It doesn't really matter which, east or west. Thankfully, one of those options is there. West. Number 2 says a current will be induced in a loop of wire in which situation. You have 4 options. Your option A says a constant current flows around a straight wire surrounded by a stationary wire. A constant current flows through a straight wire surrounded by a stationary wire. You would produce a current in the wire loop in that situation. You will not. If you have a constant current, that's going to generate a constant magnetic field. Now, if that magnetic field isn't changing, then nothing's occurring. There's nothing that's current in that wire. You've got to have one of those two conditions met. The magnetic field either has to be changing or moving, or the wire has to move in order to generate a current. We don't have any that if you have changing value, he is real similar to the negative. All right, now I can take. How many people got? Now I can take on person 3 and 4. This is a tough question. What's not so bad? You got to know the topic. That's not too bad. Please just maybe question number 4. Yes. All right, let's take a look at multiple choice 4 now. We have 2 magnets, X and Y following the top of the fast food. So just something that's 2 magnets, north pole, south pole, north pole, south pole. You would get this copper tube. You would get this glass tube. The question is based on the diagram, the correct observation between the demonstration is what? Let's look at our 4 observations. Both magnets fall in the same rate as 3 faulty voltages. Is that correct? No. We don't. We did this demonstration yesterday. The copper tube, they don't fall in the same rate. The glass is going to fall in the same rate. Check the script. The copper tube is going to fall in the same rate. Okay, let's look at E. Magnet X, which is the first one. Falls at a faster rate because of the induced current in the degrees and the force of that case. No, it's sort of not going to fall faster than the top two. That would violate the law of conservation of energy. You end up with more that to the bottom than the top. That's not going to work. That's not going to work. C. Magnet X falls at a slower rate because of the induced current in the degrees and the force of that. Does that work? Yes. X is going to fall slower because it's current in the copper tube. Why isn't it on the glass? Why don't you get this effect happening in the glass when you do copper? Not conductive. It's all depending on which conductor. It's not copper doesn't do this because it's magnetic. It's not what it's involved. Copper does this because it allows the electric current to be produced and therefore generated. It doesn't have to be plugged in to generate the field. Can't get the current to be fast. So I answered conductor as well. Copper is so any conductor will work. You've got a conductor. There's a number of things you got to break down in the building devices. One of the things is the connectivity. You want a better conductor. One of the things is the cost. Both great conductors, but way too expensive. You got to think about using the generators, right? You also got to think about the durability. Soft. Okay. Probably the biggest thing. Let's look at C. Magnet X falls in sorry, I guess we can do it. Falls in slow rate because copper is a conductor, glass is work because both magnets fall at a faster rate. No, it's not going to fall at a faster rate. It's one of them. Glass is going to fall at the same rate. Now let's take a look at question number 3. Tough one. Really tough one. How many people got question number 4 right? Yes. Question number 3 is a real tough one. Now today right now, I have seen a question like this all my life. But I haven't seen one in the last few years. It's been fortunate that almost identical. I don't know that necessarily that means that that the high degree of probability is going to be this time around. It Not that we're for the flexion that this or maybe it's just that we're supposed to okay, but you know what? No, it's adhesive. That's a good. All right, we're moving a magnet through this coil here. We want to find the direction of the induced current at position A and at position B on the left side and the right side. We know that when we move this magnet through this coil, we're going to get a current produced in this coil. In fact, we're going to find that current is going to produce a magnetic field. Now you have two magnetic fields. The first one, the magnet, and the second one is produced by the current. Those two magnetic fields have got to do what to each other? They've got to oppose the motion. They've got to oppose the motion of this magnet. So, I've drawn this coil a little bit different than you see on the blue screen. I don't think it's drawn well at all. It's difficult to see exactly what they mean. I hope you can see on the board up here what exactly you need. You've got this solenoid effectively, except they only got one loop here. The solenoid that has the wire in the front, the wire in the back, or something like this, right? These are different. Now, if we pull this magnet through from the left side to the right side, there's going to be a current produced, and that current's going to produce a field to oppose the motion. What's the polarity of this guy be? What's the polarity of this coil have to be in order to oppose the motion? This has got to be. What? Something? Is it going to be something? All right. Is that? When we put this magnet through the coil, this coil is going to turn into a magnet. It's going to turn into a magnet, just like the copper pipe did yesterday as we brought this magnet through. Well, what's the polarity going to be? We know the polarity is not going to be. It's not going to be south north like I got over there. That's wrong. It's going to be south north like this. Why? Okay. It's got to be attractive. Forget about any kind of arrow. It's got to be attractive. It's got to be in opposing forms. But if I'm moving this magnet through to the right, pulling this magnet through from A to B, the only thing that can oppose the motion of that magnet to the right is the south pole that they're pulling it back. Is that okay? Well, if the polarity of that coil is south on the right side and north on the left side, let's do that coil again. Let's stick our fingers, our thumbs, sorry, in the direction of the field inside the coil. Inside the coil goes to south and north. The field goes to south and north. Stick our thumb in the direction of that field, from south and north. Fingers are going to go in the direction of the current, which is going to be down in the front. It's going to be down in the front. Now, what's going to be on this side? Well, as they push this magnet through, push it through to the right, what's the polarity of this coil got to be in order to oppose the motion, the rightward motion of this magnet? What pole do you have to have ready to oppose the motion? If I have north right here, what's going to happen? Pushing it to the right, that north is going to attract that south. Push that to that north is going to attract that south. That's not going to be an opposing force at all. That's going to be force that helps it along. That's not going to be north. It's going to be south. Now you're going to have a north pole over here. You're going to have a going from south to north. The coil is going to have a thumb pointing towards the south pole, towards the north pole, the south and north, which is toward the right. My fingers are going to point up in front. Not back. try to translate this diagram now to the diagram you see on page question number 3. We're going to find that left diagram, diagram A, down in front, walk the back. It's kind of different what kind of improvement diagram they have here. The big unit I believe is that first loop that they have drawn down in front, up and down. The second loop that they have drawn over here, they need to be up in the front, down and down. So the first one needs to be counterclockwise. The second one needs to be clockwise. I wouldn't lose any sleep over these diagrams that they have drawn there. What we've done on the bottom there makes sense with the diagrams that I have. Never saw this on a test or on an exam. Yeah. Always actually on blue diagrams. It makes sense with my diagram. It's going to make more sense with their diagram. With their better diagram. Does it make sense? Does my diagram make sense? Does the whole analysis make sense? So always remember that it's got to be passive force. Moving to the right. Moving to the right, the only pushing it to the right, the only way to pull it back is to have a solid forward there. Diagram when pushing it to the right, the only way to push it back to the left is to have a solid forward. Once you recognize the polarity there, then it becomes just a coil rule form. Instead of the coil rule form from